Let's start with some basic properties for limits. First, limit of fx plus gx is equal to limit of f plus limit of g. In other words, limit of a summation is equal to summation of the limits. The same is true if you take f minus g. So you just replace the sign here, plus sign to minus sign, and also you replace it over here. The same is true if you take the product of two functions. So limit of f times g is equal to limit of fx times the limit of gx. And if you take the quotient f over g, you have a similar result. Now in this case, you do need to make sure that the limit of g is non-zero. Otherwise, you will be dividing something by 0. Let's look at a few more simple properties. Limit of a constant is equal to that constant. Okay. And then limit of x when x goes to a is equal to a. And then if you have a constant times a function, its limit is the same as that constant times the limit of fx. In other words, you can always move this constant out of the limit. Okay. And finally, if you take nth power of a function, and then its limit is the same as the nth power of the limit of f. When n is a positive integer, it follows from this property. So for example, when n equals 2, you simply let gx equals fx. So you have fx squared here, and here you're going to have limit of f times the limit of f, which is limit of f and then square. Okay. And then if you apply this n times, you're going to get this when n is a positive integer. But this is really true for any real number n. For example, n could be equal to 1/2. And when that happens, then this says the square root of fx, the limit of a square root, is the same as the square root of the limit. Okay. Now, in that case, you do need to make sure that fx is non-negative, because you can't take a square root of a negative number. With these properties, we can now look at some simple examples. First, let's look at the limit of 2x squared when x approaches to 3. Well, here we have a constant 2 times a function x squared. Therefore, we can apply the property we just learned. A constant times f, its limit is equal to the constant times the limit of f. All right, so we can take the 2 out of the limit. And now we have a limit of x squared. And then we can apply the property that if you have nth power, its limit is equal to the nth power of the limit. So that means this is the same as the limit square. And finally, limit of x as x goes to 3, we can apply this property. So the limit is simply equal to the number 3 in this case. So the answer is 2 times 3 squared, which is 18. Let's look at the limit of a square root of x minus 1. Well, square root is the same as 1/2 power. Therefore, we can apply the property that we learned with n being 1/2. And that says the limit is just equal to the square root of limit. Therefore, we're talking about square root of limit of the inside. And the limit of the inside, we can apply f minus g property. So it's the limit of x, which is 3, minus the limit of 1, which is 1. Therefore, the limit is just the square root of 3 minus 1, which is the square root of 2. Third example, let's look at the limit of this fraction here. Well, by the quotient property, limit of f over g is the limit of fx over limit of gx. And limit of f, we already did that. It's just the square root of 3 minus 1, which is square root of 2. And then limit of the bottom, again, we calculated here, it's just 2 times 3 squared. And the final answer is the square root of 2 over 18. These 3 examples shows a general principle. That is, for simple problems like this, we can simply plug in and get the right answer. as long as everything that we plug in makes sense. This works for all the elementary functions that we will be dealing with, including polynomials, rational functions, square root or nth root functions, like exponential functions, logarithmic functions, or trigonometric functions, as long as when you plug in, the function makes sense. Unfortunately, in most of the problems that we will deal with, the function will not make sense when you plug in, because like sometimes you plug in and you get a 0 in the denominator, and that's why you do need the extra work to resolve those issues. Let's look at an example. Let's look at the limit when x goes to -4 of this expression. Now, if you try to use the quotient property and try to take the limit of the top, limit of the bottom, and then plug in x equals to -4, and you're gonna see the bottom is 0, because -4 squared, that's 16, and then -8 and -8, so that's 0, and the top is also 0. So you're gonna have a 0 over 0 type, and you need to get rid of that 0. All right. So what you can do is to simplify the expression and then see if you can cancel out some terms. And then once you cancel, then it's no longer 0 over 0 type. Okay. So basically, you need to use various methods to try to factorize. Let me just list a few of the common techniques. One is to take out a common factor, and one is to use the so-called product sum method, and more generally cross multiplication. We're going to explain the product sum in this problem. And then sometimes we use formulas like a squared minus b squared formula, and we're going to explain that in the next page. So for this problem, let's try to factorize top and the bottom. Now on the top, if you look at those two terms, you see x is a common factor. So you can take out that common factor there, okay? And then the bottom here, you want to factorize. Basically, you need two numbers whose product is -8 and summation equals to 2. And then if you think about that for a moment, then they have to be 4 and -2. So in other words, the bottom is going to be x plus 4 times x minus 2. Again, if you multiply 4 and -2, you get a -8. If you add 4 and -2, you get a 2. So that's why this is equal to that. I mean, you can multiply it. So x times x is x squared, and then 4x minus 2x gives you 2x. 4 times -2 is -8. On the top, you take out a common factor. Okay, so take out x, and you have x plus 4 left. And now, as you can see, we have a common factor between top and the bottom, which is x plus 4. So you cancel out that. Notice also x plus 4 is the term that becomes 0 when x equals to -2. So that is really the reason why you have a 0 over 0 type. And once you cancel out that, then it's no longer 0 over 0 type. Okay? So you cancel out, and then on the top you have x left. On the bottom you have x minus 2 left. Okay? Now this is no longer 0 over 0 type when you substitute x equals to -4. Therefore, you can simply let x equals to -4, and that will give you the answer. Okay. Let's look at another example. Here we have a fraction inside a fraction. Okay. Now again, you can try to use the simply substitute x equals to 2 into top and the bottom. Well, in this case, you're going to have 2 squared minus 4, which is 0. So denominator is 0, and the top is also equals 0 because it's 1/2 over 1/2. So again, we run into the situation of 0 over 0, and we need to get rid of the 0. Okay. First, because we have layers of fraction, so what you can do is to multiply top and the bottom by common denominator. In this case, it is equal to 2 times x, because there's a 2 here and there's x here, and 2x is the common denominator. So we multiply by the common denominator, 2x. Now on the bottom, I replaced x squared minus 4 by x plus 2 times x minus 2. And this is because of a formula that says a squared minus b squared is equal to a plus b times a minus b. This is a very, very useful formula in calculus. You're going to use that a lot of times. So here a is equal to x, and b squared is 4, so b equals to 2. So by the formula is a plus b, which is x plus 2, and then a minus b, which is x minus 2. Okay, and then you multiply 2x into those two terms, so you get 2x times 1 over x. X cancel each other, so you have a 2 here, the minus, and 2 and 2 cancel, so you have x there. On the denominator, just keep it. Don't multiply 2x into this, because you want things to be factorized. You don't want to multiply it out. Okay, and now as before, we're going to look for common factors that can be canceled out. In this case, we have 2 minus x on the top. We don't have 2 minus x here, but x minus 2 is the opposite of 2 minus x. That means you can cancel out those two, and then you're going to have a minus 1 on the top. Notice also x minus 2 is exactly the reason why you have a 0 over 0 type. Okay, so once you cancel out, then it's no longer 0 over 0. Okay, so you cancel out, you get minus 1 on the top. On the bottom, you have x plus 2 and then 2x. Now at this stage, you can just substitute x equals to 2, and it's no longer 0 over 0 type, and you get the final answer. Okay, so next example, we have a limit of this expression with a square root on the top. Now again, when you substitute x equals to 3, you will have 0 over 0 here, because 9 and minus 9. And then here you have square root of 4, which is 2, 2 minus 3 is 0. So it's 0 over 0, we have to get rid of the 0. All right, you can try to factorize. But with x squared minus 9, you can certainly factorize with the formula a squared minus b squared formula that we just learned. But on the top, we have a square root, and we don't have a formula that we can apply to that. Now here is a technique that you should know when you deal with a square root in a fraction. Namely, you multiply by conjugate. So if you have a square root of a minus the square root of b, its conjugate is square root of a plus square root of b. Okay, when you multiply those two, what happened? Well, apply the formula a plus b, a minus b equals a squared minus b squared. So this becomes a squared, so square root of a squared, minus, and then square root of b squared. Okay, now square root and square cancel, so this is a, and this becomes b. Okay, so apply this idea to here. And so we multiply by the conjugate to both top and the bottom. Okay, on the top, this is like a minus b, a plus b. So apply this here. So it's a squared minus b squared. The square of a square root of x plus 1, and they cancel, so it's just the x plus 1. And then the square of 2 is equal to 4. And then you copy the bottom. Okay, now x plus 1 minus 4 is the same as x minus 3, and that x minus 3 cancel with this x minus 3. That's why you simply have a 1 left on the top. On the bottom, you keep the remaining two terms. Okay. Now at this stage, it is no longer 0 over 0 type, so you can substitute x equals to 3, and then you get a 6 from here, and over here you get square root of 3 plus 1, so square root of 4, which is 2. 2 plus 2 is 4, so 6 times 4. And the final answer is 1 over 24. Let's look at our next example. Limit of 1 over 2t minus 1 over t squared 2t as t approaches 0. If you try to substitute t equals 0, you're going to have 1 over 0 and then minus 1 over 0. 1 over 0 should be considered as the infinitive. I mean, when you think about this as a limit. So it's a infinitive minus infinitive type of limit. And we don't know what that is. We have to simplify this expression, and eventually you're going to get a 0 over 0, and then you use the techniques we learned earlier, try to cancel out the 0. Okay, so let's see how that works. For those two fractions, what you need to do is to find the common denominator. To do that, you factorize, so the 2t is just the 2t. But here you can take out a common factor t, so t times t plus 2. And now you can see the common factor. That should be 2t times t plus 2, okay? You don't have to repeat this t here because the t is already here. So that is the common factor. All right, so you're going to try to have this common factor in both terms. For the first one, you have to multiply top and bottom by t plus 2 to get this. Okay, so t plus 2 on the top, t plus 2 on the bottom. For the second one, you simply have to multiply by 2. So 2 and then 2t, t plus 2. And now as you can see, these two have the same denominator. So this is just equal to keep the denominator, and then on the top you subtract the two each other. So you're going to have 2t, t plus 2 on the bottom. On the top you will have t plus 2 minus 2. 2 and 2 cancel each other, so you have t left. And now t and t cancel. So you have 1 over this. Now this is no longer 0 over 0 type. So you can just substitute t equals to 0 and you get the answer. Okay. Next, we have the following function. This is called a piecewise defined function, and we want to determine the limit as x goes to 2. Because it's a piece-defined function, we have to determine which, whether we want to use this expression or the second expression. Well, it depends on whether you are on the left side of 2 or on the right side of 2. And that brings us to the definition of one-sided limit. Okay, so here are the two definitions. The two limits. X goes to a from the right, a plus means right. X goes to a from the left. And we have the following theorem. Limit of fx equals to L if and only if the left limit is equal to the right limit and equals to L. Okay, so basically you need to compute the left limit and the right limit and see if they match. If they do match, then that value is the limit. If they do not match, then there's no limit. Okay. All right, let's compute the left limit. When x goes to 2 from the left, meaning x is less than 2, you have to use the first expression, so minus x squared plus 6. And now this is a very simple limit. You simply substitute x equals to 2, so minus 2 squared, which is 4. So minus 4 plus 6, that is equal to 2. Let's compute the right limit. Well, this time we're going to use this expression. Again, x equals to 2. You can substitute that into here. So you got a 2 minus 1, which is equals to 1. Now, do those two limits match? No, because 2 is different from 1. And therefore, the limit does not exist. Let's look at a picture of, here is a picture of the function. So the left side of 2 is, you use this expression, minus x squared plus 6, which is a parabola. Notice that it will have a hole here because x is less than 2 but not equal to 2. Okay, and then after 2 it is x minus 1, so it's a straight line here. Okay, as you can see from the graph, the right limit approaches to here, which is equal to 1. The left limit approaches to 2, and they do not match. Therefore, the limit does not exist. All right. Our final example deals with a sine function. X goes to 0. Now, again, if you try to substitute x equals 0, I mean, this part you do get 0, but here we got 1 over 0, sine of 1 over 0. 1 over 0 does not make sense, okay? So we cannot do this by substituting x equals 0. And if you try to simplify it, really there's nothing you can simplify, because with sine, we don't have any kind of, like theorem or something that allows you to factorize or anything, okay? So if you think about this, x squared approaches to 0, okay? Sine kind of runs up and down between 1 and minus 1. But sine, it doesn't go to infinitive. So sine goes between 1 and minus 1. Therefore, this whole thing shouldn't be, it should simply go to 0. Our final example deals with a sine function. Now, if you try to substitute x equals 0, you get 0 here, no problem. But here we got 1 over 0, and that does not make sense. Okay, if you try to simplify it, there's really nothing you can do about it, because sine function, really there's no way you can simplify something like this. But if you think about this for a moment, this part goes to 0, so that's fine. But sine, although we don't know exactly what happens, but it kind of controlled in the sense that sine is no more than 1. Okay, so this whole thing is should be between 1, sine is between 1 and minus 1, therefore x squared is between x squared times 1 and x squared times minus 1. So this should be controlled by those two functions. And this brings us to the Squeeze theorem. The theorem says if my function fx is between two other functions, g and h, okay, and if the limit of gx is equal to limit of hx, and they're both equal to L, then the limit of fx has to be equal to L as well. In other words, if f is between those two functions, and both those two functions have the same limit, then my middle function f has no other place to go, so the limit has to be equal to L. Okay, let's apply this idea to our problem. So first, as I mentioned a moment ago, sine is between minus 1 and 1. Now, if you multiply both every one by x squared, then we get the following. Notice that x squared is non-negative. When you multiply by something non-negative, you don't have to reverse the direction of inequality, so you still have less than or equal to everywhere. Okay, so this shows our function is between those two other functions, and that's exactly what the setup for the Squeeze theorem. And now let's see what's the limit of those two functions. Well, that's easy to determine. The limit of minus x squared when x goes to 0 should be 0. You substitute x equals 0 here. Same for limit of x squared. So both those two functions approach to 0. Therefore, my function has to have the same limit by the Squeeze theorem. Here is the picture. The function is here in the middle. And then it is between y equals x squared on the top and y equals minus x squared on the bottom. And notice that both x squared and minus squared have the same limit here. They both approach to 0. So this middle function has to approach the same limit. Okay. that's all the examples. Let me give you a quick summary. So first, very simple-minded method. You can plug in if that works. Okay. Now in most problems that we will see, it will not work because you run into like 0/0 kind of situation. So you will need to factorize and then cancel out the 0 factor to get rid of 0. And we learned a few algebraic techniques like multiply top and the bottom by common denominator if you have a fraction inside a fraction. If you have a square root of expression in a fraction, you can multiply by the conjugate. And then we learned some formulas such as a squared minus b squared formula. And for limits involving infinity and minus infinity, you simplify it and then try to get a fraction that is of the form 0/0 and then apply the previous techniques to cancel out the 0 factor. Okay. And then for piecewise defined functions, we compute one-sided limits, and the left limit has to match with the right limit. And then finally, we have a theorem called the Squeeze Theorem, and those are pretty special and apply to certain type of functions. Okay. All right, that's all the techniques we learned. There is one topic which is limits involving with infinity. We don't cover it here, but in a different video. And in Calculus 2, people also learn additional techniques for computing limits, such as the L'Hopital's rule.